The Rogers Corporation presents Design DK, Copper Surface Roughness and Thickness Considerations for an Automotive Radar Antenna. Now here's your host, John Coonrod.
Hello, my name is John Coonrod and I am a Technical Marketing Manager for Rogers Corporation. Today I'm going to be talking about design decay, thickness, and copper surface roughness considerations for automotive radar antennas. And specifically, I'm going to be talking about PCB, printed circuit board technology, and also high-frequency circuit materials, and how these are implemented to be used in these type of applications. To start with, I want to talk about the Product Selector Guide, which is a document that's very widespread on our website, and it's a good document that shows an overview of all the high-frequency circuit materials that we offer, and a lot of the properties that are very important for the fabricator and the circuit designer to understand. So with that, let's go ahead and take a look at a portion of this Product Selector Guide. Shown here is a portion of the Product Selector Guide, and you can see on the first column there are a list of products, and this is part of the RL3000 series of materials. The column to the right of that is dielectric constant, or epsilon sub r, or relative permittivity, and you can see there's two subcolumns there. One subcolumn is labeled process, the other column is labeled design. For the process, or in other words process decay, that is actually a dielectric constant value that is measuring raw materials using an industry standard test method per IPC. It's IPC-TM-650 2.5.5C test method. It's basically a clamped resonator test method testing the raw material properties. Now, Rogers uses this test method to look at the materials for process control and quality control. Now the next column is design, or design decay, and design decay is a little different. The values that are found here are actually tested by circuit performance. So we actually make microstrip transmission line circuits of different length. We use the microstrip differential phase length method, and from that we extract the dielectric constant as the circuit would perceive it. So design decay is actually a decay value that is generated from circuit performance, or it's basically a circuit property, whereas the process decay is actually a raw material property. So the design decay is really the proper value to use in circuit design and circuit simulation. We have done many studies on copper surface roughness and how it affects insertion loss and phase response, and this essentially is how the circuit is perceiving the dielectric constant in circuit form. So it's a circuit perceived dielectric constant, which we call design decay. Now from these studies, what we found was there are several things that can slow the wave propagation. In a very general sense, an electromagnetic wave that is propagating in free space, once it enters a different medium of a higher dielectric constant, the wave will do several things. Obviously it compresses, but besides that it actually slows down, and a slower wave is perceived by the circuit as a higher dielectric constant, or a higher dielectric constant is going to slow the wave down. And what we found is there's more things than just the substrate dielectric constant that can slow the wave down, and copper surface roughness is one of those. Shown here is an excerpt from one of our studies that we've done looking at copper surface roughness. And what we did was we built 4 different laminates using 4mm LCP. So we used the exact same substrate, but we used 4 different types of coppers that had significantly different copper surface roughness. And then we tested the copper first to begin with a non-contact laser profilometer to understand what the copper surface roughness really was. Made the laminate, sent it off, had circuits made. Circuits came back, we tested them, they're microstrip transmission lines, and these are the results shown here, where the y-axis is effective dielectric constant and the x-axis of frequency in gigahertz. And what's interesting about this is there's very distinct trends here, obviously. The red curve, that is the effective dielectric constant versus frequency behavior of the circuits that use the smooth copper, and that copper had a surface roughness about 0.5 microns RMS. The green curve is circuits that use copper that was a little rougher, about 0.7 microns RMS. The magenta curve a little rougher, and then the blue curve was the circuits that use the roughest copper at 3.0 microns RMS, which is considered very rough. Now, if you look at the range of dielectric constant value in this chart, there's a range of about 0.3, and that's very significant, especially when you consider all these circuits use the exact same substrate. It's all used in the 4mm LCP, and the only difference is copper surface roughness, where the smoother copper, the red curve, that really does not impact the phase velocity much, so the wave didn't slow down much. But the blue curve, where the copper is very rough, it did slow the wave down a lot, and again, the slower wave is perceived by the circuit as a higher dielectric constant. There are several different dependencies for design decay. There is thickness dependency, frequency dependency, as well as copper surface roughness dependency. So to start, let's talk about thickness dependency. Essentially, a thinner circuit is going to be more affected by copper surface roughness effects than would a thicker circuit. And I kind of like to think about it in a very intuitive way. And that is, if you think of a microstrip transmission line that has a signal conductor on top, ground plane on the bottom, what you see is on a circuit that's very thick, the separation between the signal plane and the ground plane is very far apart. So the copper surface roughness is not really going to have much impact. However, if you look at a circuit that's very thin and the signal plane and the ground plane are very close together, then the copper surface roughness really does impact the phase velocity, and it can impact the design decay. So let's take a look at a chart now that actually shows this in a little more detail. The chart shown here is a decay versus frequency chart, and in this case the decay on the y-axis is the extracted dielectric constant. This is not effective decay. This is actually the dielectric constant extracted from the circuit performance. And then the x-axis is frequency, going from about 1 gigahertz out to 50 gigahertz. And what's interesting here is we're using the exact same materials. This is the RO3003 laminate using half-ounce ED copper, and there's 3 different curves here. The green curve is the circuits that were built and extracted the decay from for using the very thin laminate, 5 mils thick RO3003 laminate. And then the blue curve is the exact same material again except thicker. This is 10 mil thick laminate, and then the red curve is 20 mil thick laminate. And you can see as you have a thicker circuit or a thicker substrate, the design decay curves are actually shifting lower and lower down. And if I were to make a circuit that was 50 mils thick, 50, what you find is the curve would approach the number of 3.0. Because once the copper planes are far enough apart, in the case of a thick substrate, now the copper surface roughness does not impact the phase velocity or the design decay. And really what happens is it's really reporting the intrinsic dielectric constant of the material. And in the case of the RO3003 materials, the intrinsic or the bulk decay is 3.0. So once you get thick enough, the circuits are really performing with the dielectric constant of the raw material only, and the copper roughness is not having an effect. For 77 gigahertz automotive radar applications, they're very commonly using thin circuits or thin substrates, and that's really necessary for several reasons. One thing is when you get to higher frequencies, the millimeter wave frequencies, there's different issues, and a thinner circuit will allow you to have better RF performance. And that's because the thinner circuit has less radiation effects, radiation loss. Also, a thinner circuit will be less likely to have spurious wave propagation modes, and also you can have less problems with unwanted resonances. So a thinner circuit basically allows the designer to have more consistent RF performance at millimeter wave. Now, a thin circuit is also more sensitive to copper surface roughness, of course, and a thinner circuit that's used at millimeter wave, it really should be considered very closely what type of copper is used. So in the following chart, I talk about and show the effects of copper surface roughness of 2 different types of copper used on 5 mil RO3003, which is the material that is predominantly used in the 77 gigahertz automotive radar sensor applications. The chart shown here is the dielectric constant versus frequency chart for 5 mil RO3003. However, it's using 2 different coppers. So the blue curve is showing circuits that were using the standard ED copper, which is actually very commonly used in the 77 gigahertz automotive industry right now. And then the orange curve is the same circuits except using rolled copper, which is very smooth. Rolled copper has a surface roughness about 0.4 microns RMS. The ED copper has about 2.0 microns RMS. And at 77 gigahertz, the design decay for the ED copper version is about 3.16. And at 77 gigahertz, the version with the rolled copper, it's very smooth. The design decay is about 3.03. So you can see that the very smooth copper, even though it's a thin substrate and it's sensitive to copper effects, the very smooth copper is really not affecting the phase velocity much. So the circuit really is perceiving the bulk decay or the intrinsic decay of the material of about 3.0. This now concludes this video for design decay considerations. Thank you for watching.
For additional information and technical tools, if you are not already a member, join the Rogers Technology Support Hub and gain access to calculators, technical papers, and more of Coonrod's Corner and other informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.